His picture is outside the door. Alex's, that poster was prepared by my wife just for the conference. Alex passed away within the last month, right?
I think March the 5th,
March the 5th.
but we didn't learn about it until April 5th.
Yeah, 2 months ago. And Alex spent many months at LSU. I met him repeatedly in the 1990s. I think the first time I met him was in Berkeley in 1991, spring semester in 1991. So it's sad to see him pass, but his work lives on.
Okay, so our first talk is Ramiro Lafuente-Rodriguez over the specialization order on the prime spectrum of an algebraic frame.
So good morning. I would like to thank the organizers for letting me give this talk. This work is in progress. I have started this in Colombia, where I attended a conference in topology, in which they talked about the specialization orders, and it just called my attention that this order is interesting when you have a spaces T0 but not T1, and the spectrum of the prime spectrum of an algebraic frame is T0, and usually well, you can find examples that is not T1. So this order can live there, and we can find there interesting stuff to work on. So I will go over a brief description of the basics. Well, a frame is a complete lattice in which we have an extended distributive property. A prime number, prime element in this frame is essentially a reducible element. I will go through 2 examples along my talk. One of them is the set of all divisors of 24 and the prime elements here, which are 3, 6, 8, and 12, which are the reducible ones. In the set of all ideals of the integers, the ideal generated by prime powers or by powers of positive powers of prime numbers are exactly the prime elements. We turn our attention to compact elements, which are defined this way. So if they are, if C is compact, if it's less than or equal to the sup of an arbitrary family of AIs, then you can always find finite number of these AIs. So that C is less than or equal to the sup of these finite elements. Okay, and we call these compact elements K of L. Well, we call spec of L the set of all primes of L, and we put a topology there. We call it the Hull-kernel topology. By defining these sets for every A in L, U of A is the set of all prime elements that are not above A. And we will show that the collection of all these U of A's, where A is compact, is an open base for a topology in the spec of L, in the spectrum of L. We need to technical lemmas. The first one basically tells us that there exists a maximal element with respect to not containing a given compact element. And the proof is just a routine an application of Strom's lemma. The second one is telling us that the infimum of all times is 0. Okay, I will not go over the proofs, but just to see that we're using this first lemma, we can basically prove the second one by defining the set SK similar to U of A, and prove that this is when we take the infimum is 0. Okay, this is a very technical theorem, but I would say more than technical is essential because this will allow us to prove that the U of A's are basically are the basic forms an open basis for our topology on the spectrum. So the empty set is there, the whole space is there. That's 1 and 2. Number 3 is essential because you know that whenever we have a closure for the FIP, the finite intersection property, you can always build a topology. You can always define a topology. So this third one is really the crucial to define a topology. Then we have 2 nice ones, the 4th and the 5th statements. Essentially that we can play with the U of A. This 5th one allows us to prove that if we consider U as an operator, then this is an injective one. Okay, the proofs. Well, the proof of each one of these is pretty much straightforward, except I would say the 4th one. I remember that when doing this 4th one, this took me a while, and actually Papia helped me to prove the most difficult part. That is this one. This one here, the converse. So this is for number 5. This is not that trivial. It requires a little bit of work.
Shouldn't it be lower?
I'm sorry?
Shouldn't it be? Because aren't you, if B is less than or equal to A, and I take something that doesn't exceed A, then it shouldn't exceed B. Oh no.
So you're talking for number 5?
Yeah, is that correct?
Yeah.
Okay.
Yeah, that's accurate. Yeah.
In full, the equation for the U is U of the bracket.
Oh, that should be.
All right,
just AI.
that should be just A.
It should be
Yeah.
just AI there in number. It's the U there is.
There's an extra U inside the parentheses on the line.
Oh, yeah.
It's not that next,
The other
yeah,
one.
there.
Yeah. Oh, there is an extra U here. There's a typo here. There's an extra U. Yeah, sorry about that. Yeah, there's an extra U. All right. Okay. Yeah, the proofs are pretty much straightforward, except that inequality. The one that includes an inequality. Okay, so here in this theorem, we're proving that when we take the U of A's where A is a compact, then this will form a base for our topological space. So I will not go over the proof, but this is essentially this theorem is completely based on the previous one. On this one. So basically, considering 3 and 4. Okay. All right. So we need to know how the how the open sets of this topological space look like? Well, the good thing is that they behave very well because every open set in the spectrum of L is of the form U of A, where A is not necessarily compact. It can be any element of the lattice, which is good. All right. The proof, again, is not that difficult. I will continue with some, explain some properties of algebraic frames. Well, a lattice is special when it is the lattice of open sets of some topological space. And it happens that when L is an algebraic frame, then L is always special. And
Can I ask, we forgot maybe to insist, are you assuming the top element of L is compact?
yes.
Okay.
Yeah. So, and this is specifically when L is precisely it's when we consider the open sets of the spectrum of L, the prime spectrum of L. So we take its open set and we take this new this function that assigns to every U, to every A, it's precisely the open set U of A. Okay, so the spec of L is T0, which is interesting that we will use this fact, and then we will show that the effect of L is not necessarily T1. Okay, C is compact, then U C is compact in the spec of L. Yeah, recall that L is compact whenever the top element is compact. So this can be expressed as the soup of compacts. Okay, so yeah, L is compact if and only if the spectrum of L is compact. And this happens for algebraic frames. All right. Okay, here we have some particular examples of lattices for Boolean algebras. If we take complements, then this translates to complements in the open sets U of X. So in this particular case, the U of the complement of X is precisely the complement of U of X. This is basically what this lemma is saying. Okay, and therefore a spectrum of B, when B is a complete Boolean algebra, is T2. And therefore, since all the elements, all the basic elements are open and closed at the same time, so the spectrum of B is zero dimensional. So it has a basis of properties. All right. Two other properties for any topological space X. The set of copings is an algebraic complete Boolean algebra. And furthermore, if P is an algebraic complete Boolean algebra, then the spectrum is compact, half-solved, and extremely disconnected. I am not sure about the terminology, but some guys call these Stonian spaces. When a space is compact, half-solved, and extremely disconnected. Stonian, okay. All right, so let's talk about preorders. So we define a preorder in any topological space with no assumptions so far. So X is less than or equal to Y if X is in the closure of the singleton Y. And it happens that when X is T0, then this is a partial order. And when it is T1, it's not interesting at all, right? Because when it's T1, every singleton is closed. So X is in the closure of Y, it means X equals Y. And so we are not doing anything interesting. It's interesting to see that when F is a continuous function from X to Y, then this function that goes from X, from the, not the topological spaces, but from the orders, considering the orders, then F is order preserving. All right, let's see what happens with the specialization order on D24. So it happens that we, with these 3, 6, 8, and 12, all the primes in D24. So 8 keeps isolated, and then we have a chain, 3, 6, and 12. And this happens, interesting, in a very interesting way, this happens, it happens something similar when we take the frame of all ideals of the integers, which are principles, right? And we said that the primes are positive powers of prime numbers. So it happens that we have we have a bunch of chains, a countable number of chains, 2 and all its powers, 3 and all its powers, 5 and all its powers going down, and so on. So this is what we get when we define the when we endow the specialization order on this frame. So this looks interesting to me, and there are some questions here. One of them in which I'm working in is well, what happens when we take a PID, a principal ideal domain? So what will happen when we put the specialization order? And I suspect, I'm still working on that it will behave this in a very similar fashion. Okay, so we have one open question there. To have more insight into this question, I would like to know exactly how the closure of a singleton looks like, and that's property number 8. In this lemma, 1 through 7 are basically what we have seen in that previous theorem in which we established the properties for use for the open elements, for the basic elements of the spectrum. These are basically for the complements. And the new one is this 8th one, which allows us to determine how the specialization order will behave. All right. So there is an interesting property here, that there is a Galois connection between the spectrum of L with its own order and the same spectrum of L with the one is just the other one, but you just flip it you put it upside down, and that is what is happening. So there is indeed a Galois connection between them, and the proof is just the use of this property 8, basically. All right. So as we suspected, when we have that B is an algebraic complete Boolean algebra, then when we put the specialization order, we get something not interesting at all. The trivial order. Okay. Some people call this specialization order the Alexandrov order. Logicians call it that way. And it happens that, well, what's an Alexandrov space? It's when it has the IIP, the infinite intersection property. So when we have space with a finite space, then this is not interesting. It will always be Alexandrov. But we want to see this property in a particular space. So that is the spectrum of an algebraic frame. That's the whole point. Some properties about Alexandrov topologies is first countable, locally compact. And this is telling us, this theorem is telling us that there is a one-to-one correspondence between Alexandrov topologies and preorders on sets on X. So if we take an Alexandrov topology here, and we take the same set with with some preorder, then there will be a one-to-one correspondence. All right. So the spectrum of L is not always Alexandrov. And here's the example that I was able to come up with. We take the algebraic frame of all ideals of the ring of integers, which you know are prime powers, prime powers. And we take this family of opens and we look at its intersection. Well, it happens that if you build the intersection on that chain of powers of 2, it will go to 0. And on the other side, you have all the powers of other, let's say, the odd powers, or the powers of odd primes, excuse me. And they will, in the intersection, they will remain those and the 0. But that's not an open set. That's not an open set. So this was a bit sad for me because I really expected it to be Alexandrov, but it is not. It's not. And so the next step here is, well, the question arises naturally. Is this true for a PID? So I guess yes, but honestly, I didn't come up with a proof yet. So hopefully soon I will be able to prove it. That's all I wanted to show.
Ramiro,
You mentioned complete Boolean algebra, which was an algebraic frame. Did I get you right? That was one of the topics that you mentioned.
Yes.
So what are the atoms there? Excuse me, what are the primes there? Are they just the atoms?
Not necessarily. Not necessarily. because you can take the, if you're turning this upside down, so you're considering the atoms. I'm considering the, like the maximal ones.
The coax.
Yeah, okay, but you can take one atom and then a chain that is below it. And so these are primes as well. Yeah. These are primes as well. Yes.
What was the one-to-one correspondence between Alexandrov spaces and what other thing? I missed that part that you mentioned.
The Alexandrov spaces and?
Yeah, you mentioned that there was a one-to-one correspondence. What was it?
Okay, so you take, there is a one-to-one correspondence between, you take an Alexandrov space X and any preorder on X. You define any preorder the way you want,
Okay.
and there will be a one-to-one correspondence. Yeah. Thank you.
So next talk at 9:40, 6 more minutes. We're free to go. Don't go.
Yeah. Just make it easy.